So this summer I had an REU position at the Mariah Mitchell Observatory, which is on Nantucket. And for my project, I looked at a star with the exceedingly memorable name of Mount Wilson Catalog 349A. It's in the constellation of Cygnus, and it's unique because it's currently in a very short stage of its stellar evolution, and it's a stage that we don't really know anything about. We don't even know how old the star is. We do know that it's not a main sequence star. It's either very young or very old because MWC 349 has a circumstellar disk. Here you can see how the disk is sort of constraining this material from expanding and creating this hourglass structure. However, if you zoom out to larger scales of about 3 arc seconds, you see that the structure goes away and you're left with more of a blob or square, which is why it's really weird that when you zoom out to extremely large scales of like 9 arc minutes, it looks like the structure comes back. It has the same waist and sort of the same orientation, but one of the things that we were wondering about was, is this really caused by the star, or is this larger structure caused by the surrounding clouds of cold gas? So we mapped those clouds in carbon monoxide, and then we sent our data to Dr. Begin here, who made some really nice contour maps and overlaid them onto this image. And what we found was that these clouds don't bracket the structure really at all. And so that suggests that the structure on this large scale is caused by the disk. It could be that MWC 349 is a really old star and that it is periodically shucking off some of its mass, so we would see it at large scales and at small scales, but not really in between. But that's not the cool thing about the disk. The really cool thing about this disk is that it is the only known natural laser. It doesn't look like that. The actual laser is a laser in the infrared, and it's caused by light from the star traveling through the disk towards us. Unfortunately, since it's an infrared laser, you can't observe it from the ground. You would need a space-based telescope or SOFIA, so that wasn't part of my project. However, the disk also has masing regions, which are in the radio, and those you can observe from the ground using the 12-meter and the SMT. And when you get spectrum of the masers, it looks like this. The spectra is double-peaked because there are 2 masing regions, one on either side of the disk. There's a blue-shifted one because the disk is towards us, and then a red-shifted one because the disk is rotating away from us. And the intensities of these 2 peaks... Oh, my laser died. Okay, so the intensities of these 2 peaks change over time. A student the summer before me took a bunch of this old data that we had and plotted it, and he found that the maser peak-to-peak ratio had a period of about 238 plus or minus 8 days. But the plus or minus 8 days is really problematic because after a couple years you can't predict what the period is anymore. And so part of what I did this summer was take data that wasn't so spaced out, that was more closely put together to try to constrain the period. And we ended up with 6 data points, which looked like this. Doesn't show up too well, but... and there's definitely a trend going on, but it's not enough for us to get a period just from this alone. And it's too far away from the old data for us to use this to constrain the old data. And so right now we're waiting to get some more time, to get some more data points to constrain our period. The other thing I was able to look at was the optical light from the star, which is also really weird. Most stars have spectrum that look like our sun's. There are a lot of absorption lines in them. But MWC 349 doesn't have any absorption lines. And that's not because they're not there. It's that they're masked by massive emission lines that originate in the disk. The largest of the emission lines is the H-alpha line. And one of the things we were interested in was seeing how the emission from H-alpha changed as opposed to just the flat continuum. So to do that, we used 2 filters. We used one centered on the H-alpha and one centered on the adjacent continuum. And we took this filter and subtracted it from this filter, and that left us with just this emission. And then we were able to plot the H-alpha emission and the continuum on the same graph and compare them. And when we did this, the most interesting thing we found was this, where the continuum decided to just go absolutely insane, something that it hadn't really done before, and something that wasn't going on in the emission at all. And we tried to explain it. We are still trying to explain that. And my last day there, I was at my final meeting with my advisor, and we were looking at this graph, talking about causes of this large variation, whether or not this anti-correlation here and this one over here was real, or if it was an artifact from the way that we used to find the H-alpha emission. We were looking at this graph, we were looking at the original H-alpha filter, and then we noticed that if you were to add a couple points right here, this would look sort of periodic. So we subtracted this downward trend that you see, and we found that it does indeed look really periodic, which was exciting. This is something that nobody had ever noticed before, and we found it 3 hours before I had to leave. So I took this and I fit a Fourier series to it, because I figured anything periodic should be able to fit a Fourier series. And I found that it had a period of 234 plus or minus 4 days. You'll remember that the period for the masers is 238 plus or minus 8 days. So it seems really probable that what's ever causing the variations in the peak-to-peak ratio of the masers is also causing the variations in the H-alpha emission. So once again, it's really important for us to get those extra data points for the masers, because not only will we be able to constrain that period further, but we'll be able to compare directly the two periods and see if there's any sort of delay between the two periodicities. And then if there's a delay, this will tell us, since we know roughly where the masers are being emitted and roughly where the H-alpha is being emitted, the velocity of the mechanism that's causing this periodicity. And if we know its velocity, we can guess at what it actually is, which will tell us about the structure of the star, which will, in turn, tell us a lot about its physical structure and what sort of phase of stellar evolution this is, and, if it's old or young. Thank you. So I went through that really, really fast. Are there questions? Yeah.
How do we know that it's a natural laser, since we needed a space-based telescope to figure that out?
Versus like an unnatural laser, or versus something else?
Well, how do we know that it's a laser source? Because you were saying that.
The same way that we know that something's a maser source. So I don't have the spectrum from the laser, but if it's a laser or a maser, you're going to have a fairly narrow full width half max for your peak, and so it was narrow enough that you could say that's definitely amplified versus just regular emission. Mm-hmm.
I guess I'm confused how you have such H-alpha emission like that. Is it displacing at that wavelength, or
you mean?
How is it?
You mean this?
I didn't realize it's because it's so unique.
Yeah. It could. I guess it could either be that there's just a lot of hydrogen in the disk, or it could be that of the light that the star is giving off, a large portion of it is at just the right wavelength to excite what hydrogen there is in the cloud, which is kind of bad, because we'd like to know about the composition of the disk or the composition of the star, and it seems to me like this could go either way, so I don't really know much about it.
So this is the disk. Do you know what inclination the disk is at?
We're pretty sure that it's almost edge on, just because of where we see the masers and the laser.